Hello friends, welcome back for this class 2 module 5 of metal coatings of experimental stress analysis. This is Professor Mayur Pawar along with Professor Venkatesh Casey and Professor Surav Krishnan. So let us start class 2 of this metal coating. So today's topics are refrigeration technique. Next is load relaxation for compressive stresses. Next we will see about crack detection methods. After that we will see advantages, disadvantages, and at last metal coating technique. We will start with the refrigeration technique. So in low stress regions it is possible to obtain coating cracks by employing refrigeration techniques. First the specimen is loaded until the stresses in the critical region is just below the yield stress. The coating is subjected to a rapid temperature drop while under load. The rapid temperature drop produces a state of hydrostatic tension in the coating, which is superimposed on the existing stresses, which are usually sufficient to produce coating failure in the crack pattern. The direction of the resultant cracks is coincident with one of the principal stresses, that is sigma 1 and sigma 2, due to the load, since the isothermal stresses have no preferential directions. In this way, we can check out refrigeration technique. In order to reduce the temperature of the coating, two methods are employed. First one is ice water is used. Ice water is sponged over the area of the coating which has not previously responded. This method is not very much successful. The second one is steam of compressed air is passed through a box containing dry ice, and then it is directed onto the surface of the coating module. The steam of very cold air can be accurately directed and the resulting crack patterns can be closely defined. We move on to the next topic, that is load relaxation for compressive stresses. Metal coating does not respond to compressive loads. In order to overcome this difficulty, a relaxation technique is applied. First of all, a load is applied to a coated specimen before it had opportunity to dry. The load is maintained on a coated specimen until drying is complete. Under this condition, the coating is stress-free. The specimen is highly stressed in the compression. When the load is released, the specimen will stretch since it was previously compressed, and tensile stresses will develop in the coating, which are sufficiently high to indicate regions of compressive specimen stress. Next topic is crack detection methods. There are three crack detection methods. First is focus and light source, second is static flux method or electrified particle inspection, and third is dry etching method. So when a load is applied to a specimen treated with a metal coating, cracks will form in the coating. So if this coating is properly applied, these cracks will remain open to the loading is to apply the coating for either directional information or stress level data accurately. It is necessary to locate all the cracks and to record the value of load at which they occur. So we see first focused light source. In this, the crack produced in the metal coatings are very fine. In order to observe these fine cracks visually, a focused light source must be directed at oblique incident to the surface, and which should be normal to the crack. For observing small areas, this is a very good method. For observing large area, this cannot be employed. Static flux method, which is also called as electrified particle inspection. In this method, water containing wetting agents are used to reduce its surface tension, is applied to the coating which is to be examined. If any cracks are present, the wet water flows into the cracks, fills them, and makes electrical contact with the metal specimen. The surface of the specimen is then brought to dry with the facial tissue. This drying process removes the water from the surface of the coating, but does not remove the water from the cracks. Next, a talcum powder negatively charged is sprayed through the special gun onto the specimen. The negatively charged particles of powder are attracted electrically to the groundwater containing in the crack. The powder forms small white modes over the cracks and provides an excellent means of location of the crack patterns means that it will look like white lines. Next, third method is dry etching method. In this, the dry etchant is a mixture containing turpentine, machine oil, and red dye. The etchant is applied to the surface of a cracked brittle coating for approximately 1 minute. During this time, the etchant begins to attract the coating in the neighborhood of the cracks, thus making them very wider. If the etchant is left in contact with the coating too long, it will attack the surface of the coating. After the etchant is wiped from the surface of the coating is cleaned with an etchant emulsifier. The emulsifier is soap and water generally. The dye which has penetrated the cracks is not removed during the cleaning process, thus the crack appears as a fine red lines on a yellow background. A fine red line is due to the red dye. Before moving on to advantages and applications, we will see the brittle coating technique. So there are some 10 steps. First, we should prepare a surface, that is our surface preparation, and we have to coat, which is called as undercoat. Then we have to select coating material or coating. Then how we should apply that coating comes in the next step. Then we have to leave for drying. Then we have to calibrate that. Then we have to test. Later we have to detect and record crack patterns. Then we have to post clean, and at last we should do computations. So firstly, surface preparation is done. All the oil, grease, or any other material which might affect the bonding of the resin coating must be removed. Grinding rough sand casting in the areas of stress concentrations improves the visibility of the crack patterns. Sand or grit blastings is normally required for surface preparation prior to ceramic coating. For the sanded coat, an aluminium undercoat is often used in the air dried coatings to improve the visibility of the crack patterns. No undercoat is used in the ceramic coatings. Then, in the next step, a proper coating selection is done. Resin-based coating are selected on the basis of temperature and humidity, except at time of test. Ceramic coatings are selected on the basis of coefficient of expansion of the material under test. Then application of the coating. So pressure cans or airspray guns are used generally to apply both resin-based and ceramic coatings. Color is normal gauge of coating thickness in the resin coating. Then normal drying time for resin coatings is given in order of 24 hours to permit sufficient time for solvent release from the coating and development of the coating materials. The ceramic coatings are ready for use after they have cooled from the firing temperature. Then calibration is done. The calibration parts which have been sprayed and dried along with the test parts are loaded as cantilever beams with a no deflection and calibrating fixture. Strain scales are then used to measure the strain at which the coating begins to crack. Then calibration of coating also predicts how the coating part will behave during the test. It is useful to obtain this information before testing a part and learning that the particular coating is too soft and requires excessive strain to initiate crack patterns. Sensitizing and coloring techniques are also rapidly evaluated by calibration and by using calibrating fixture. Then you have to test that. Time required to reach load is a prime consideration in the use of this resin coating. The coatings creep rapidly, so loading time should be as short as possible. Temperature changes during test should be minimized, as this also affects coating sensitivity. Oil should be kept off as a part which will attack the resin coating. This limitation is not applied to ceramic coatings. Then at last we have to detect and record crack patterns. For that we have the crack patterns in the resin coatings are being the oblique lighting spread on the pattern with increasing the increments during matte coating. These boundaries markers are used isotheltics and represent approximate constant strain curves. The crack may be colored with a red dye or they may be brought out by use of an electrostatic charge particle technique, as we have seen charged particles must be used to show cracks in the ceramic coatings. Then the resin coatings may be removed by scraping, brushing, vapor degreasing or solvent. The ceramic coats are best removed by sand or filtered plastic. So this is about post cleaning of that coating. Then at last we come to that. Cracks from all the calibration bar are compared to those on the part which quantitative data are equal. Computations are done and the crack patterns are studied. We'll see the advantages of brittle coating. So this brittle coating provides whole field data for both magnitude and direction of principal stresses and does not require a radius point point for that. And this brittle coating does not require the construction of actual model and can be used actually on a prototype of actual machine component which is to be studied. There is no role of simulation problem here. The data analysis is very simple, as you have seen. Just we have to give only coating number, specify, and we have to see the crack patterns. Coming on to application of this brittle coatings. The first application is the determination of the stresses in conjunction with the coordinating method. The next is determination of dynamic strains, determination of compressive strains by using the relaxation technique. Then we can detect strains at high temperature up to 320 degrees centigrade. Then yield and plastic strains can be determined. And these brittle coatings are used for outdoor operations. Then can also be used under water and hydrostatic pressure operations. Then at last for determination of strains on very thin components also these brittle coatings can be used. With this we have completed this full chapter of brittle coatings and of module 5. Thank you.